For the last segment in this section, we'll be going down the right-hand side of this decision tree at the end of section 6. We've been doing hypothesis testing. The left-hand side is the single sample hypothesis testing. You know, it might be helpful, and you don't have to do this, but just to make a note to yourself that the left-hand side would be using a paired sample or a paired two-sample for means. Going down the middle, on the left-hand side here, we'd either be using an equal variance t-test or an unequal variance t-test. Obviously, a paired, if we have two samples that are paired, we use a paired two-sample t-test. But then we get up here to the population difference. And in this case, we're going to assume that the two samples are independent. So we're going to be using an independent t-test to test the population proportion differences. And typically, if it passes the approximation for normal test, n times the sample proportion is greater than 5, and n times 1 minus the sample proportion is greater than 5. That's right here. And the sample is usually large enough, and the variances of the two samples are similar. So in this column right here, we'll be using an equal variance t-test. So in section 7, we have this example here in the notes that says, for several years there's been an advertising war between two of the largest firms that market insect-killing sprays. A consumer agency recently set up a test to determine if one spray was more effective than the other. Two large containers, each with 1,500 insects, were sprayed according to the manufacturer's instructions. One was spray A and one was spray B. After 10 minutes, the number of live insects were recorded for each container. There were 90 survivors in container A, while the container sprayed with A, and 120 survivors in the container sprayed with B. We want to ask the question, is there a difference between the two sprays, or is there evidence at an alpha equals 0.01 level of a difference in the killing effectiveness of the two sprays? Since the sample size is large, we can use the z-test for the two proportions. But what we're going to do here is use actually the computer in this example, and we're going to create the data set by creating two columns of zeros and ones representing live and dead insects. So we follow the 6-step process as before. In this case, we're comparing the proportion of the first to the proportion of the second. So this is similar to an independent t-test, but we're exchanging the means for a proportion. So we're asking, are the proportions of the first minus the proportion of the second equal to 0, or there's no difference? Or the proportion of the first minus the proportion of the second not equal to 0, which means there is a difference. We don't know if A is more than B or B is more than A, we just know there's a difference. Now notice that we explicitly said that our alpha will be 0.01. We're looking at a 99% confidence interval. So we select the t-statistic, calculate its value. We identify the critical values for the t-statistics, and let's do that using Excel. So I'm going to start with a blank sheet, and in spray A and spray B, I'm going to create the data set. So I'm going to make a 1 represent the number of live insects in the container sprayed with A. There were 90 of those. I do have the single row for my label, so I'm going to go down here to the 91st row. And then for the insects that were dead, I'm going to represent zeros. It started with 1,500 insects, and so I'm going to go down here to row 1,501, and the 1 is just because I have a label in my first column. Now for spray B, we have 120 live insects. So I'll take this down to 121. And then the rest are zeros. I can just double click right there and it's going to automatically copy all the way down. So I wasn't given a data set, but I can create a data set. In this case, it's a proportions test, so I need to create two proportions, the proportion in A and the proportion in B. And I go to my data analysis, and I go to my t-test to sample assuming equal variances. The range for the first set of data is A1 through A1500. I could have done this a little bit easier. And then for the second, I'm just going to learn from my mistake and put in how many cells I want to go down. My hypothesized mean difference is 0. We leave that blank. I do have labels. But now we have an alpha 0.01. So I need to change my significance level in this case. And then I'm going to put the output here on the same page. Now the nice thing about these videos is if I'm going too fast in the videos, you can pause it and run the test yourself and do those things on your own. Now, what do we find? We find in spray A there were only a 6% survival rate, where spray B there was an 8%. Now 6% is less than 8%, so why can't we just naturally say that A is more effective than spray B? Well, because there's going to be, this is just a sample. And remember, a sample is, we're making an inference or an estimation about the population. So we know there's going to be natural variances around our sample means. What we want to know is there an enough difference between the killing effectiveness of A to say that it's actually more effective. That's where we run a t-test. So the t-test for this test is -2.14. That just means that the mean proportion for A is less than the mean proportion for B. We compare that to our t-critical. Now notice that in this case our alpha was 0.01, so our t-critical is not 2, it's actually more than 2. At an alpha of 0.01 or a significance level of 0.01, we find that our t-statistic, the absolute value of our t-statistic, is less than our t-critical. So we would fail to reject the null hypothesis. Now, given that we fail to reject the null hypothesis, what does that mean? Well, in my notes I say retain. I like the word fail to reject, but retain is okay. We just would never say that we accept or prove the null hypothesis. So we make a decision related on this. We make a business decision related on this information. And we would say there really is no statistically significant difference between the two insect sprays. So even though brand A killed in this sample 2% more bugs than brand B, we can't say that the difference is something other than just natural variation in our sample. Now one could say, well, let's retest. But remember, when we go back and retest or return to the first two steps of our hypothesis testing process, what we're essentially doing is increasing our alpha error. We're increasing the probability of rejecting a true null hypothesis. So it wouldn't be good science to retest in this case.